Welcome to this explainer. You know, if you've ever looked at a circuit board and just seen a chaotic jumble of wires and resistors, well, get ready to see it completely differently. Today, we're going to reframe the seemingly dry math of electrical circuits and look at it for what it truly is, a fascinating, beautifully contained universe governed by strict, unavoidable cosmic laws. We're going to uncover the invisible order that dictates exactly how energy moves through our world.
Okay, here's our roadmap for today. 1. The fundamentals of electricity. 2. Kirchhoff's universal rules. 3. Combining circuit resistances. 4. Power and energy transfer. 5. Real-world component behavior. And 6. The microscopic view. Let's dive right in.
Section 1. The fundamentals of electricity. To navigate this electrical universe, we really have to establish our fundamental lexicon first. You can't understand the poetry of a circuit if you don't know the words, right? So let's lock down our 3 core concepts.
First up is electric current. Just picture electric current as the traffic flow of charged particles on a highway. It's that simple. The higher the rate of flow, meaning the more cars passing a certain point every second, the higher the current. It's all about that movement.
Next, we've got potential difference, or as we usually call it, voltage. If current is the traffic, potential difference is essentially the push, or the pressure, driving that traffic forward. As these charged particles get pushed along, they transfer energy from one point to another. Literally, no push, no movement.
And finally, there's resistance. Just like the word implies, this acts as the physical obstacles. It's the narrow lanes or the roadblocks slowing down our flowing traffic. It measures exactly how difficult it is for our charged particles to pass through a specific component. Now watch how this conceptual definition turns into a clean, indisputable mathematical reality. Current, represented by the letter I, is literally just the change in charge, or delta Q, divided by the change in time, delta T. It is a pure rate of flow, perfectly quantified. Similarly, we can calculate that push, our potential difference. Here, V is found by dividing W, which is the total work done or energy transferred, by Q, the charge itself. This tells us exactly how much energy each little unit of charge is carrying with it as it moves between 2 specific points.
And this brings us right to Ohm's law. Resistance is exactly equal to voltage divided by current. It's the ultimate balancing act. It shows how resistance ties our voltage and current together in a perfect ratio, provided, of course, that physical conditions, like the temperature of our wire, stay perfectly constant.
Section 2. Kirchhoff's universal rules. All right, now that we have our basic vocabulary locked in, let's get to the narrative pivot of our explainer, the universal laws that dictate absolutely everything happening in a circuit.
Here's the thing you really need to grasp. Kirchhoff's laws are absolutely not just arbitrary equations you have to memorize for a test. They are profound, fundamental statements about the universe itself. The first law relies on the conservation of charge. Whatever current flows into a junction must flow out. And the second law relies on the conservation of energy. The energy provided to a closed loop has to perfectly equal the energy dropped across it. Together, they state unequivocally that charge and energy can absolutely never be created from nothing, and there's no way they can be destroyed.
Let's see this in action. Because energy is strictly conserved, the sum of all the potential differences, or voltage drops, across the components in a series circuit must equal the total voltage supplied by the battery. The math isn't just a polite suggestion. It is an inevitable expression of a cosmic rule playing out on a miniature scale.
Section 3. Combining circuit resistances. Let's see how these foundational laws build into real problem solving by deriving the rules for combining resistances.
So imagine you're taking a path through a complex parallel circuit. It probably looks pretty intimidating, right? But actually, scratch that. We can solve for the total resistance completely logically by following 4 simple steps. And the best part is, it all stems directly from what we've already learned.
First, thanks to Kirchhoff's second law, we know the voltage is exactly the same across parallel branches. Because that push is identical, we can use Ohm's law to write distinct equations for the current flowing through each individual branch.
Next, we apply Kirchhoff's first law, conservation of charge. We know the total current is simply the sum of the currents in the individual branches. When we substitute our Ohm's law equations into that sum, we end up with a shared V, or voltage, across the board. And by factoring that supply voltage out, this complex derivation suddenly feels like a breezy, elegant, logical puzzle.
Just look at how beautifully that simplifies. By isolating the resistance terms and finding the reciprocal, we arrive perfectly at the classic foundational formula for total resistance in a parallel circuit.
1 over total resistance equals the sum of 1 over each individual resistance. It's definitely not magic, it's just the inevitable consequence of energy and charge conservation.
Section 4, Power and Energy Transfer. Now, equations and derivations are fantastic, but humanity didn't master electricity just to solve math puzzles on a whiteboard. Electricity is ultimately about transferring energy to do actual physical work in the real world. Lighting our homes, heating our food, and powering the devices we use every single day.
We know power is the rate of energy transfer, calculated as voltage multiplied by current, or P equals V times I. But by substituting Ohm's law into that base equation, we create a highly versatile toolkit. We get P equals I squared R and P equals V squared over R. This brilliant trio of equations lets us calculate energy transfer and power output, no matter which specific variables a component actually gives us.
Section 5. Real-world component behavior. Let's introduce a little real-world messiness to our explainer. Up until now, we've been assuming perfect conditions, but physical materials often bend our perfect mathematical rules when they heat up or when they reach their limits.
Think about the stark difference between an ohmic conductor and a semiconductor diode. The perfect straight line of an ohmic conductor reliably obeys Ohm's law forever. But the semiconductor diode, it stubbornly resists almost all current until it hits a specific threshold voltage, and then suddenly the current skyrockets in a sharp curve. It perfectly illustrates how the physical properties of a material can really alter those mathematical ideals.
Section 6. The microscopic view. For our grand finale, resuming all the way in, we're transitioning our perspective from the abstract diagrams of a circuit board down into the atomic lattice of the physical wire itself.
This brings us to the drift velocity equation, and honestly, it's spectacular. Notice how this formula reveals that the massive, macroscopic currents powering our world are entirely dictated by microscopic, almost unimaginably small elements. Lowercase n for the charge carrier density, V for the average drift velocity of those colliding particles, and A for the cross-sectional area of the wire. The macro is entirely dependent on the micro.
We've seen how length and material dictate resistance. So as you digest these rules of the universe, I want to leave you with this provocative thought. If a wire's resistance scales uniformly with its distance, constantly stealing away power as heat, how does humanity actually manage to efficiently power sprawling cities from power plants that are hundreds of miles away? Think about the absolutely colossal engineering required to overcome that fundamental cosmic rule. Thanks for joining me on this explainer, and keep questioning the universe around you.